Skit.
Yes.
Okay, now we're good to go.
Okay. So welcome everyone to this next session on white box obfuscation and logic locking. We're going to have 3 talks on white box, 2 talks on obfuscation, and 1 on logic locking. And the first talk is by Sylvain Goulet, and it's called Structural Attack and Repair of Diffused Input Blocked Output. Diffused Input Blocked Output white box implementations. So please, Sylvain.
Thank Eduardo for this introduction. So during this 5-minute presentation, I'm going to advertise this work. So indeed, it's about attacking and fixing a white box cryptography paradigm, which is called diffused input blocked output white box crypto. Okay, so I will just make a brief overview over our results. So we formalize what is DIBO, so this diffused input blocked output paradigm to protect block ciphers in a white box context. Then I will explain what are the distinguishers, all right? And we believe it's the first time actually we come with a mathematical proof of cryptanalysis for white box crypto, meaning that it will work for sure with 100% of success, okay? So whatever the randomization in the white box, and then I will, we explain the repair, okay? So typically in this work, we studied the T-box, which is, it takes a byte and it turns it into a word, so 32 bits, through an S-box, and then we have some the mixed columns coefficients here that most of you know about. And so this is obfuscated in white box with the phi over there, which is a linear function, 32-bit to 32-bit, invertible, and B, which is a bijection, which can be nonlinear. So for you who are more visual, so the T-box is this part, and so we have here the linear function phi and the nonlinear parts, which are 8 by 8. Just because next to the T-box, then we will have to XOR operations according to the bytes, and so this bijection B must be blocked, okay, but into 4 bytes. And actually, so the vulnerability, let me spoil a little bit, comes from the phi here, because phi is invertible. But if now I consider only 8 bits of output of phi, and I consider the linear operation, that is the composition of the T-box, or only the linear part of the T-box, and the 8 bits here, this is an 8 to 8 linear function, which sometimes happens not to be invertible. Okay. So the typical attack in practice consists in trying to reverse, making all the key guesses. So we reverse the T-box, and when the key is good, we end up with only the DIBO, which is preceded by the linear part of the mixed columns. Okay, as I just said, this function x here to any of the 8 bits, so feeding B1 or B2, etc., might not be invertible. Okay, and that will be an issue we will exploit. And otherwise, you see, when we make a wrong guess, so this C is non-zero, so K star is the good key, which is concealed by the white box, and K is the key guess. So in this case, we have a function which is much more complex than a DIBO, okay? And so we might not detect that. So the state of the art is a work, published at FSC in 2016 by Sastrich and other authors, which came with a distinguisher. And so we improve on top of it. So basically, they consider the weight of a spectrum, so absolute values. And actually, we refine this distinguisher by only counting the positions where the spectrum is null. Okay, so we don't care about the values. We just look I would say to the support of the spectrum. Okay, so that's a difference. Okay, so we make an extensive comparison in the paper. So just to give you some highlights, we have a distinguisher which is motivated because the number of zeros is characterizing so the linear part through the bijection here. So we have put the mathematical results in the paper. And actually, you see, the fact that our distinguisher works implies that the former distinguisher works as well, okay, using some Cauchy-Schwarz arguments. Okay, so just quickly to illustrate how good it works. So for a wrong key, we have this number of zeros in the Walsh spectrum, whereas for the good key, it's way more. And you see, so there is no overlap between this red area and this green area, which we can formalize. So we have bounds, which definitely show that there is no such overlap. And so we can distinguish for sure. Okay, so that's the main result. Now, just to finish on the countermeasure, so to make the attack impossible, it's pretty simple. We just want to avoid the linear functions Li, so there are 4 of them, okay, the 4 that feeds the 4 bijections at the end. We need to make them invertible. It's as simple as that. So if we take for phi the obfuscating linear part a random 32 by 32 matrix, if you wish, the probability that we are not in the situation of the countermeasure is very high. You know, 99% of the time, my white box cryptography implementation will be vulnerable to the spectral attack. Okay, so we need now to restrict a little bit the conditions on the phi, and so we end up in the complementary of this proportion, and our attack is no longer relevant. Okay, so just to conclude, we have a new distinguisher, so based on a spectrum analysis of the white box tables. It is we have a proof for the cryptanalysis, and this proof allows us to derive a countermeasure. Okay, so I just would like to acknowledge a Brain European project, as well as mentioning that the methods for the cryptanalysis have been already included in a catalyzer tool. Thanks a lot for your attention, and looking forward also for you to see what's going on at ISO, because there is a technical report which is published on this topic. Thanks a lot.
Okay. Thank you, Sylvain. Do we have any questions? So I think on the Sulip there are no questions yet, but I had one. And it's so the countermeasure is so in this case is to select these matrices such that they are invertible, right? So they are usually randomly generated when we're generating the white box. But this would mean that the set from which we get these matrices becomes much smaller, right? Than if we just choose them completely randomly. So in to which extent are reverse engineering attacks made easier if we select exclusively invertible matrices for these linear operations?
Mm-hmm. Yeah, good question. So actually, we counted them exactly in the paper. So the number is reduced clearly, but roughly speaking, we keep 1% of them, but the number of such linear permutations is actually already extremely huge. So taking 1% is not it's not decreasing this number, and so we still have plenty of entropy to hide the key.
Okay. So, okay, thanks. Yeah, any other questions? So okay, so maybe later, if by the end of the session somebody still wants to ask something, we will still have some time. So we can go to the next talk, and it's by Yui Koike, and it's called Yoroi Updatable White Box Cryptography.
Yep. Can you see my slides?
Yes, thank you.
Okay. Okay. So thanks for the introduction. Hi, I'm Yuji Koike. So the talk is about your updatable white box cryptography. This is a joint work with Takanori Isobe. So white box cryptography aims to ensure security of cryptographic keys in the white box setting. In this setting, the adversary has access to all the states, including inputs, outputs, and internal states of the algorithm. Under such assumption, there are two requirements to design a new white box cipher. The one that I'm going to focus on is code lifting security. This security prevents code lifting attack, where the adversary tries to steal the whole implementation code for the cryptographic function and use it as a large effective key in a standalone manner. There exists several ciphers which tries to satisfy the requirements, such as SPN box by Bogdanov et al. There are three things that I want to emphasize about the existing ciphers. First, white box ciphers are table-based ciphers, which means ciphers look up tables repeatedly to encrypt data. Second, the table consists of inputs and outputs for block cipher. And finally, the table is treated as secret key, and it is a target to mount code lifting attack. To provide code lifting security, SPN box has security property called space hardness. For example, SPN box 16 provides T/4 128 space hardness, which means the adversary has to gain at least 1/4 of the table, which is 32 kilobytes, to successfully compute inputs with probability of more than 2 to the power of minus 128. In other words, T/4 128 space hardness ensures that leakage of partial key data does not affect security. However, space hardness is just mitigation, because if the leakage continues, then the amount of leaked key data will be beyond T/4. Even worse, eventually all the key data will be stolen, and as shown in the figure, security level Z drops to 0. So in order to ensure constant security, it is necessary to update the table before the leakage amount reach T/4. However, in white box cipher use cases, this could cause two problems, which are computational cost and security risk. First, regarding the computational cost, updating the table means it requires re-encryption of data in the system. Second, concerning the security risk, encryption gives more chance for the adversary in the system to see the data in the plain text form. Because right after decryption of data with the old key, they are in the plain text form. So if the adversary stays in the system, it is possible to see them. So to solve these problems, we defined a new property called Z longevity, which keeps upper bounds for code lifting security less than 2 powered by minus Z, while maintaining same functionality at every single point. And to ensure longevity, we designed a cipher which keeps same functionality even after table update. Table updates help to keep security level so they can prevent code lifting attack. Also, maintaining the same functionality can remove re-encryption. To design such cipher, we took several approaches. First, we combined encryption algorithm EKI and decryption algorithm DKI with table S to create tables. When combining them, we applied EKI to the partial outputs of S and DKI to partial inputs for S. More importantly, in this approach, the partial outputs which goes through EKI directly goes to DKI and skips MDS layer or any other layer between EKI and DKI. and the rest of the outputs from S goes to the layer between them. In order to update the table, we update the key KI for EKI and DKI, and we do not update the key for table S. By this approach, we can keep the functionality, because even after the table update, EKI and DKI will be canceled out. So this is the general construction of Yoroi, which we designed. And this construction is based on the approaches that I talked about before. And we put 10 round AES at the end of the algorithm to simplify some security evaluation. And this is a case study where we assume the 24 megabytes data leakage of table for Yoroi 32, whose table size is 48 gigabytes on a daily basis. In this case, by repeating the table update at proper timings, Yoroi can provide 128-bit security, and therefore it can ensure 128 longevity. And here is the performance results. And as shown in the figure, when compared with the existing ciphers highlighted in red, Yoroi is still competitive. And here is the summary. And in this work, we proposed new property called Yoroi longevity, and we designed a Yoroi which ensures longevity. Thank you.
Okay, thank you, Yuji. Do we have any questions? Let's see, Sulip, not yet. So, well, I would have one now. These space hard ciphers, if I understand correctly, they basically the larger they are, the more difficult they are to code lift, right? Because
right.
It's more difficult to transmit them over the network and so on. So do they also have some property of locality, or do they, as they become larger, do they also become slower?
Yeah, actually, yes, because a table consumes a lot of memory. So sometimes it cannot be loaded in L1 cache, but it has to be loaded in RAM memory. So in that case, the performance will be slow as the table gets larger.
Okay. Yeah, and do you think there's any possible modifications for such ciphers in such way that they don't necessarily become much slower as we make them larger? Like, is there any alternative design strategy that comes to mind?
Right now, no, actually, yeah. So that could be a further direction, yeah.
Yeah. I think I also thought it could be interesting.
Yeah.
Okay. Do we have any other questions? So I actually have another one, but maybe I can ask them. I can ask it in the end of the session in case we have more time. But so maybe we can proceed with the next talk. It's by Okan Seker, a white box masking scheme resisting computational and algebraic attacks. So please.
Hello again. I hope everything is working. Thank you for the introduction. And my name is Okan Seker. And today in this session, I will talk about our joint work with Thomas Eisenbart and Marcel Iskevich, a white box scheme resistant computational algebraic attacks. So now we have a good white box introduction before, and I would like to actually start with Palantry, the seeing stones of J.R. Tolkien, because I think it's a really good example and I like it. So I will not be able to give the full details, but the simplest intention of these devices is the communication in Middle Earth. So, but one should be careful while using this device, as they are possessed by Sauron, and he actually owns the device. He can affect the mind by his whispers and can even read the deepest secrets. Now, when we take a look to our model, we actually see exactly the same adversary. The cryptographic implementation resides in a fully hostile environment. The adversary has full control over the device, can inject faults in an inspect memory and aims to recover sensitive information. And this is why we need white box cryptography. However, today all the academic proposal has been practically broken against such a strong adversary. So in this work, we tackle this problem and propose the first combined masking scheme that can resist state-of-art white box attacks, computational algebraic attacks, which we will give brief introduction in the following slides. So we provide a novel composable to proof for security. So we take a look at two notions in cryptography. The first one is probing security against computational attacks, and the second one is the prediction security against algebraic attacks. We provide a novel composable to proof for prediction security of our construction, and moreover, we supported our results with the verification tools by Birikov et al. For prediction security and MaskVerif for probing security. And finally, we give a proof of concept AES implementation to analyze the overhead of our security features. So let's deep dive into the state-of-art attacks against white box design. The first attack is based on a well-known physical attacks on embedded devices. The idea is actually the same as such an analysis. The only difference is the source of your traces. In this version, the adversary can simulate the power traces by software execution traces. Here these can be the memory accesses, intermediate values, or written read values. And security against these attacks can be captured by the probing model, where the adversary can obtain t intermediate variable per execution, where t is a fixed integer. Now let's take a look to the algebraic attacks, which is another hit for masking on white box systems. The idea is to first finding a window that contains the secret shares corresponding to a value that can be predicted. Then the question is finding a linear combination of these nodes that give you this predictable value. Of course, if we look at the quadratic combinations of these nodes, we will result in a higher order algebraic attacks. And prediction security capture the essence of these attacks. Adversaries can obtain all intermediate variables, but can only use a deed order function to combine them. Now, while we are talking about how can we implement masking on white box systems, the algebraic attacks actually break our every hope. As you can see from the previous slides, we don't need to consider the masking order. The attacks works on every order as long as the masking is linear. Therefore, the Boolean masking, no matter what the order is actually vulnerable to all algebraic attacks. And now, what we take a look to the previous security notions, the probing security and prediction security, we cannot actually, we need actually both of these notions. Although one of the notions seems to cover the other, they're actually incomparable, and we need both notions in our proof. And this is why two countermeasures were proposed on top of each other to prevent attacks in earlier works. So let's go into the construction. Although now what we learned from the previous attacks is the following. First of all, we need a regular masking scheme to eliminate regular secret sharing to eliminate the computational attacks. And secondly, we need to increase the decoding order at the same time. Okay, let's see how can we do it. Let's remark the Boolean masking as in the left-hand side. Now the question is, how can we increase the decoding order? So the idea is simple. Let's share a share. Let's say x0 with a multiplicative masking, such that x0 is a product of d+1 random values. And the rest of the shares stay the same, and we denote this masking by ND sharing. And here you can see that decoding function, the order of the decoding function is indeed d+1. So as a regular masking scheme, the data transformation should be followed by the gate transformation, and we provide secure XOR and refresh mask gadgets. And the foundations of this gadget are actually the same as Boolean masking. And however, we need to be careful about the intermediate variables that deals with x0. Let's take a look at the basic example of XOR operation. Here you can see, besides the last share, everything is sharewise. And in order to secure the correctness of the gadget, we need such a variable as we defined here as u. And here you can see a concrete construction for first and second order XOR operations. In the same way, we can actually define the operations for AND and refresh mask operation. So in the final part of our short presentation, we would like to take a look at the proof of concept AES with a performance comparison. Here you can see the light blue line corresponds to the previous masking schemes where we need to combine two different masking schemes to get the desired security level. And the bottom line corresponds to the regular masking scheme where there is no nonlinear component. And now we can see that due to the structure of our scheme, it's efficiently increase the security of our structure in dimension of n. However, the nonlinear order is the bottleneck of our scheme. And when we take a look at the randomness, we can actually see a similar result with respect to a better result with respect to using two different masking scheme. So in conclusion, here you can see our summary of conclusion. Thank you for your attention. If you have any questions, please feel free to contact us. Or if you're interested, you can find more details on our ePrint or in our long version of the video. And if you're interested in the verification codes or analysis code, please check out our GitHub page, where you can just find the required code for the verification and analysis. Thank you.
Okay, thank you, Okan. Yeah, any questions? Let's see. So, okay, then I'll start. Yeah, so in this scheme, where does the randomness come from?
Yeah, so that's actually one of the things that we actually need to deal. So here we actually have a randomness source, and one thing we need to sure is actually we need to have a secure or a reliable randomness source. That's something we need to assume, and this is actually derived from the input, and it's actually fed into the encoding and also the circuit itself.
So basically, the PRNG maybe has some additional secret, and then
yes,
every time you input something different, you generate like a different pseudo-random value, right?
Yes, exactly.
Okay, nice. And yeah, so I assume the design, like if you want to make it complete against such automated attacks, maybe it still needs some DFA countermeasures, right?
Yeah, we in this version we didn't actually think about the DFA. Yes, we need additional countermeasures for fault attacks also. Yes, sure. This is just for the like we can think about the passive attacks, the computational algebraic DC and regular DC.
Okay, yeah. Okay, nice. Yeah, any other question? Yeah. Okay, maybe let's go with the next. There's one.
No.
So does this masking scheme have a resistance against fault attack? Yeah. So was it the same one? So I think what happens is that since for every input message you generate the same random, the same pseudo-random value, then in the fault attacks you usually perform them with the same input message several times, right? So I think that
I think I mean we can combine with the state of art fault attacks countermeasures, but I mean one has to be careful because we are actually living in a little bit more dangerous environment, a white box environment. So my first intuition is to like we need definitely some other layer of countermeasures for fault attacks.
Okay. And there's one more from Alexei. Thank you for your work. So the general combined schemes is very interesting. Do you have concrete candidate constructions for higher degree, like degree higher than 3 instances, even if without proofs?
I mean, yes. I mean, so we can actually define. So now the problem is the extending from the previous work to second order is especially for the composition was not straightforward. And yes, we can definitely define individual gadgets, but when we think about the combinations, like for example, now I think it's a little bit more details, but when we think about the combinations, we can actually get 2 different gadgets, and if we have a third order combinations, we can just use second order combinations from one gadget and one order combination from the other one. This requires, I think, a little bit more detailed theoretical work on it. In a just a structural way, yes, we can just increase here. We can actually use and define an N3 masking scheme, but for the security of it, we need to be like the proving should be, I think, is not straightforward. And I mean, even just in an iterative way, we can define the prediction security for or the algebraic security for the third order, but the proof of it, I don't think it should be a straightforward proof, I should say.
Okay. Thank you, Okan. If
Thank you
anybody
very
has
much.
more questions, you can write them on Tulip, for example.
Yep. I will be on the Zulip, so thank you very much.
Okay, thank you. So let's go with our next talk. It's by Max Hoffman, and it's called Doppelganger Obfuscation, Exploring the Defensive and Offensive Aspects of Hardware Camouflaging.
Yes, thank you. So hi, everyone. And yeah, let's get going with this sneak peek to our paper. So on a very high level, when talking about engineering, we refer to the process of getting from some high-level description to some finished product. And reverse engineering is the way back. So analyzing a finished product to get some understanding, some high-level description back out. And if you want to protect against reverse engineering, the go-to method is obfuscation, which kind of has the goal to make to not impede the engineering part, not make it much harder, but get the reverse engineering to insanely difficult. Very hand-wavy, but this is kind of the goal. And if you think about obfuscation, you most likely think about the traditional logic level obfuscation, which takes something like this electric pole here and transforms it into something that is much harder to understand, but still has the same functionality. And if we take a look at the big picture in terms of hardware reverse engineering, where you would take a chip, extract the netlist, so the kind of the circuit diagram, and then analyze it to get an understanding, this traditional logic level obfuscation makes the understanding part really hard. But of course, keep in mind that with enough time and money, it will definitely be broken. So since all the information is in the netlist, an attacker with enough resources will eventually understand the design. What we now focused on in this paper is low-level obfuscation, which is still an obfuscation scheme, but with a different paradigm or core principle, because on the outside, the design or whatever you obfuscate still looks the same as the obfuscation happens on a lower level that is maybe not directly observable. And with this approach, we kind of make the recovery of the netlist itself harder. So the understanding part, the analysis takes place on an incorrect or incomplete netlist. And in our paper, we provide the first generic obfuscation scheme that is based on this low-level obfuscation itself and analyze both the defensive but also the offensive potential of such low-level obfuscation schemes. And in a nutshell, Doppelganger basically enables you to create a design that has a certain visible functionality, the one that a reverse engineer will find, and a hidden functionality, which is different, but which is the one that is actually executed. So we get an asymmetry between what a reverse engineer sees and what is actually computed. Of course, this says this is not arbitrarily different, but details are in the paper. And Doppelganger is applicable to every encoding logic. So whenever you have a structure like on the right, under some condition you output one symbol, under another condition you output another symbol, you can apply Doppelganger. And this is, of course, applicable then to the transition logic, for example, of state machines, bus address encodings, and so on and so forth. And the building block we base this on are camouflaged gates with dummy inputs, for which both like scientific and even industrial instantiations exist. And the workflow is basically that the designer designs both functionalities, the visible one and the hidden one. And the Doppelganger algorithm then creates one design that houses both of these functionalities. And the core principle or the core difference here is that instead of adding new signals or circuitry, as is common for obfuscation, we obfuscate by ignoring existing signals. And then to check or demonstrate that this is actually applicable in a defensive scenario, we tried or we applied the Doppelganger technique to a cryptographic coprocessor design. where we chose as the hidden functionality, the encryption in CBC mode, but as the visible functionality, it appeared to a reverse engineer that there's actually the CFP mode used. And the cool thing here was that we only had to modify 4 signals. So you don't have to dive into the details of the state machine now, but only 4 signals had to be connected to these dummy inputs of camouflaged gates to facilitate the obfuscation. And there was no observable overhead. So without obfuscation for different design parameters and with the obfuscation, we are still in the same ranges of area. So it's not immediately suspicious. And then we also swapped sides and took the point of view of a malicious designer and had the goal to insert now a stealthy but exploitable hardware Trojan into this very coprocessor. And like motivations like include backdoor for covert access or like pressure or bribery. And we wanted this design to appear genuine. So now the visible functionality is the crypto coprocessor with no changes, but the hidden functionality, the one that is truly executed, houses an active Trojan. And the properties here is that a Trojanized chip would still work fine with an untrojanized implementation, but an attacker can just from observing the message stream extract the key. And here again, we managed to do this by only manipulating 6 signals in the whole design, again, being undetectable area-wise. But we also showed that our Trojan is invisible during reasonable testing. So all testing that is standard industry practice would not detect this Trojan. So the only chance is reverse engineering, but by design of the doppelganger technique, where an analyst would only find the visible functionality, the Trojan is not even part of the netlist. So all netlist-based Trojan detection schemes would be ineffective here, and no suspicion is raised during the standard analysis approaches. So in conclusion, we showed that the doppelganger obfuscation technique is quite effective and quite resource preserving or inexpensive. But at the same time, such low-level obfuscation can be used to craft quite dangerous Trojans, or in general, is quite a dangerous tool for attackers. Thank you for your attention. And for more details, please have a look at the full version of the talk or the paper.
Okay. Thank you, Max. Any questions? Do we have? Okay, so I was wondering. So you gave this example of how you obfuscate AES in a certain mode. And so if I understood correctly, you basically make it look like it's AES on a different mode, right? So if I want to obfuscate something simpler, like if I just want to use AES as a pseudo-random function, for example, wouldn't it? Yeah, because the nice result is that this didn't demand much overhead. But if I want to obfuscate something much simpler, wouldn't I be forced to make the circuit look a bit more complicated, and then this would indeed add some notable overhead? Or is that assumption incorrect?
Yeah, so of course I hadn't the time now to go into all the details, but doppelganger is only applicable to these encoding logic blocks, let's say. And the most prominent example here are the state transition functions of state machines. And these state transition functions, if you think about them, they anyway make up a very, very small part of your design. It's really just the feedback logic of the state register of a finite state machine. The feedback logic of this you would obfuscate, which anyway consists of like maybe double-digit number of combinational gates. So the main parts of your design, all the functional blocks, they remain unobfuscated. So if an attacker is only interested in seeing what blocks are used, this technique will not help you. But in understanding the logic in a sense of the sequence of operations that are controlled by the FSM, here doppelganger can really help and does not differentiate between between what design you have at hand. So even if you have a very small design or a very large design, you can apply it anyway on something that is always kind of equally sized. Hope this answers your question.
Okay. Yeah. Yeah. Okay. Thanks. Okay. Anything else? Anybody else? There's one question in the chat. So to Max, does the doppelganger project only against particular reverse engineering techniques? Does the doppelganger protect only against particular reverse engineering techniques? In principle, could an adversary dig deeper and find the invisible part, especially if the adversary knows that the circuit is protected using doppelganger?
So doppelganger itself does not rely on any specific instantiation of these camouflaged gates. It only needs dummy inputs. However you build them doesn't really matter as long as you are able to build dummy inputs to your combination of gates. And then, of course, if an attacker knows which of those are used and knows that doppelganger is applied, they most likely could deobfuscate this quite efficiently. What we kind of require for the technique in the paper is not that dedicated deobfuscation methods do not exist, but that they are too expensive to apply just preemptively without any suspicion. And we have some papers there in our paper listed that show that for existing instantiations, we have, for example, deobfuscation methods that then have an overhead of like 14 times per gate. And something like this, you wouldn't apply preemptively on your whole circuit, right? And then our argumentation is that doppelganger does not raise suspicion from the first second, unlike other obfuscation techniques that, for example, have an overhead in size of like 3, so really make your state machines insanely huge or something. This is directly a red flag. But doppelganger kind of requires you to go through the whole reverse engineering process. Then you will find that something is off, and only then you will have to get back to the drawing board and repeat a majority of your process to really understand the design. And as I said, obfuscation will anyway be broken at some point in time with enough time and money. This is really like the optimal result, to require the attacker to really redo a lot of the reversing process and invest a lot more time and money.
Okay. Thanks a lot, Max. If anybody has more questions, please write them on the Sulip or on the chat. So let's go to the next talk. It's by Florian Stolz, Lifeline for FPGA protection, obfuscated cryptography for real-world security.
Yes, thanks. You should see the presentation now, right?
Yes, thank you.
Okay, so hi, my name is Florian Stolz, and I will now quickly talk with you about our paper, Lifeline for FPGA protection, in which we built an IP protection scheme based on obfuscation. So let's quickly talk about our motivation. So we basically analyzed the current situation, and we realized that many products use FPGAs, especially in the security relevant domain, such as medical devices or in aviation. And many companies use pre-made IP cores to drive down the development costs and the time to market. However, recent developments made it easier for an attacker to circumvent IP protection schemes so they can use the cores without paying for them. Or even worse, he might do a design manipulation which can harm the user. And this can be contributed to, for example, vulnerable bitstream encryption engines and advances in understanding the bitstream format as well as understanding netlists. And to showcase this, we performed a case study on an industrial solution, and using static analysis, we found a way to circumvent it and unlock the IP core, even though it should have not been activated. So in our paper, we proposed a scheme which does not rely on the security of the bitstream encryption engine and also not on the secrecy of the bitstream format. Instead, we want to use obfuscation, first of all, to increase the effort for the attacker, but also to make it flexible and adaptable to as many FPGAs as possible. And in our special case, we are using hardware-software co-obfuscation. So we employ a soft core which coordinates the authentication and the interactions between the hardware modules. And this creates a strong dependency which again increases the effort for the attacker. And in the next slides, I will talk about the obfuscation primitives and our solution. But I already want to tell you that when you combine all these primitives together, we can defend against static analysis, dynamic analysis, as well as design manipulations. So now I will give you a quick overview of Lifeline. So as you can see, we have the authenticator and the IP core, and there's no physical connection between them. And actually, we use our first primitive partial reconfiguration to leave out the IP core after the initial startup. So the attacker cannot analyze it. And only after the authentication, the IP core is successfully configured onto the device. As I said, we use a soft core, and the soft core is running a key generation, and the key is then used to decrypt the partial bit stream of the IP core, which is then configured into the area. And of course, the software is also obfuscated using state-of-the-art methods. Now, to trigger the partial reconfiguration, we connect the RISC-V core to the reconfiguration controller. And this also allows us to do obfuscated data flows inside the authenticator and integrity checks. Now, to find out if we are running on the correct FPGA, we need some kind of identifier. So we use a unique device ID. This can be a PUF, or in our example, we use the Xilinx device DNA. And to hide from the attacker how the RISC-V core interacts with this device ID, we used our primitive crosstalk. So crosstalk is an analog effect, which allows us to transmit data between two subcircuits without any physical connection on the FPGA, so something like a radio, so that it works. And lastly, to protect the attacker from, for example, faking the device ID or doing any manipulations of the wires inside the authenticator, we developed BIMAT, and it stands for bitstream manipulation detection. And with this, we can check the integrity of wires in the authenticator on a very fine scale. So let's quickly talk about the security of Lifeline. As I already said, the IP core is only correctly configured after the authentication. So if, for example, the device ID is wrong, or we detect that the attacker changed the wire or is eavesdropping, the key generation is affected, there will be a wrong key, and this will, of course, lead to a broken IP core later. As I said, we can achieve obfuscated data flows using partial reconfiguration and crosstalk. And lastly, we can check the integrity, as I said, with BIMAT. And as I also said before, the software is obfuscated using state-of-the-art tools, but for more information, I would like to refer you to our paper. So this whole construction actually leads to a chicken or egg problem for the attacker, because the attacker cannot analyze the software in isolation. The software relies on the hardware interactions. So he needs some kind of simulated hardware. At the same time, he cannot analyze the hardware on its own because all the interactions between the modules are coordinated by the software. So we basically force the attacker to analyze the whole solution at once, which again increases the time he requires to break our solution or to find a way to circumvent it. But of course, in our paper, you can find a more in-depth analysis of the security of Lifeline and also on the strength of our obfuscation primitives. So in conclusion, in our paper, we first analyzed the state-of-the-art of IP protection schemes and showed several weaknesses under a real-world attacker model. We then built obfuscation techniques based on already known principles, such as partial reconfiguration, but also novel primitives like crosstalk. And then we showed how we can combine them to protect against a real-world attacker and how we can build an IP protection scheme based on this. So that was basically all from me. So thank you for your attention, and I'm of course open for questions.
Okay, thank you, Florian. Do we have any questions? So I have one with regards to the authentication step that you perform there. What happens there? How is that performed? Is it because you said you use some device authenticator, some fixed device authenticator, right? So what happens, or can you tell us? Yeah.
Yeah, so when a customer wants to use an IP core, he needs to send a request to an IP vendor with the device ID. And you can use, for example, the Xilinx device DNA, which is already burnt into every Xilinx FPGA. But if this is not available, of course, there are solutions which can use paths. And yes, this is one of the main factors which influences the key generation. So if you are on the wrong FPGA and there's a wrong ID, there will be a wrong key. But the key generation is also influenced by the integrity information. So we spread the integrity check temporally. So we don't do a full readback of the FPGA, but only of special parts of the authenticator, which we can define before. So we can say, okay, this part is very important for us. We don't want the attacker to, for example, change the wire connection between the reconfiguration controller and the RISC-V core. And this information also feeds into the key generation. So this then, so the correct result then depends on both the device ID and also the integrity of the environment.
Okay, yeah. But is it like a signature what is generated for authenticating or a MAC?
No,
or?
We only generate a key for a decryption algorithm which you can choose. So you can implement any decryption algorithm, and the key is then used to decrypt the partial bit stream of the IP core. So the authenticator has access to an encrypted partial bit stream, but never to the plain partial bit stream. So if the attacker changes something, we still decrypt the IP core, but of course the key is wrong. So there will be a broken IP core, like some weird sort will happen.
Okay, cool. Okay, thank you. Thanks, Florian. So then let's proceed with the last talk of the session. It's by Nimisha Limaye, and it's breaking. It's called breaking cast lock and its variant by exploiting structural traces. So I think we cannot hear you, Nimisha. Yeah, enough.
Can you see me and hear me and see my screen?
Yes, now we can see. Now we can see.
Okay, perfect. All right. So hello everyone. My name is Nimisha Limaye. I am a fifth-year PhD candidate at New York University, and this is a joint work with Abhijit Sengupta and my advisor Oscar Sinanoglu. In this pitch, I will first motivate the problem which logic locking aims to solve. Then I will touch upon a proposed attacks on the defenses published in Chess 2020. And let me quickly start my pointer. Okay. So to understand the requirement of logic locking, let's take a step back and first understand the problem at hand. Okay. So until 1980s, a vertical approach was used for design and manufacturing, and the hardware IP was developed in-house. So the design house had access to their own trusted foundries as well as testing facilities. So in short, there was a complete control over the IC supply chain. However, there was a flip side to this. As the technology went shrinking at a rapid pace, the cost of owning and commissioning a fab has proved to be extremely expensive. And as can be seen from this figure, the landscape of the current day supply chain is truly globalized. The design of chips take place in one country, the fabrication in another country, and the testing and packaging in a third country. And it is estimated that a single joint strike fighter component changes hands 15 times before its final installation, which has led the DoD to think critically about the security and trustworthiness of the ICs, especially destined for military applications. Since there's so many parties involved, and if we assume that all the concerned parties are untrusted, it leads to a diverse threat landscape. Let us assume the attacker is now interested in stealing the design intellectual property. Now, this can be achieved by illegally copying and reproducing the chips without authorization. Now, this is termed as IP piracy. The design IP can be stolen during fabrication by an untrusted foundry, or it can be obtained by reverse engineering the chip by an untrusted end user. Now, several techniques have been proposed to protect the design IP. And logic locking is one holistic solution that protects the IC supply chain end-to-end. The attacker with access to the original design can easily pirate the IP or overproduce the ICs. Now, with logic locking in place, the IP owner can conceal the functionality of the original design by adding these extra key gates controlled by additional key inputs. Now, only when the correct key is applied, the locked design functions correctly. Thus, without the knowledge of the secret key, the attacker cannot obtain a correct functionality of the design. And only authorized users like the design house can know the functionality. However, around 6 years ago, a powerful attack was proposed which broke the all existing locking techniques, and it required only a working chip and a reverse engineered netlist to extract the secret locking key. The SAT attack was basically built upon SAT solvers to prune out multiple incorrect keys with every SAT run, and this ultimately broke the logic locking techniques. Subsequently, efforts were then steered toward this powerful attack, and several defenses were proposed, which were, however, short-lived due to advanced attacks. Now, in this slide, CAS-lock and MCAS defenses were proposed in test 2020 to thwart all the existing attacks, including the powerful SAT attack. CAS-lock utilizes a cascaded structure, which, when combined with the original defense, forces the SAT attack to prune out exactly one incorrect key per SAT run, thereby pushing the attack limits to exponential. And as an extension, a mirrored CAS or MCAS defense was also proposed, which thwarts removal attacks which were evident on CAS-lock defense. So if we remove this defense, if we remove this CAS-lock circuitry, we obtain the original circuit. So that's why in MCAS, what they do is that we modify the original circuit such that if we remove the CAS block, we are ultimately left with the modified circuit as opposed to the original circuit. However, in our work, we consider these unbroken defenses proposed at test 2020 and identify several vulnerabilities in the hardware implementations to launch our attacks. We propose 3 attacks in total, 2 on CAS-lock and 1 on MCAS. The IFS attack on CAS-lock is launched using an oracle to directly extract the original design, whereas the KBM SAT attack or the key bit mapping SAT attack is launched to extract the secret key, again using an oracle. However, our IFS SAT attack, which we launched on MCAS, is launched without an oracle. And this is again to recover the secret key. Lastly, our IFS and IFS SAT attacks are successful on 14 out of 15 circuits, while a KBM SAT attack is successful on all the circuits. Now, in conclusion, we saw that CAS and MCAS were theoretically secure against SAT attack and all the other attacks. However, we identified several vulnerabilities when they were implemented in hardware. And on that note, I invite you all to refer to our teacher's paper for more details. And you can also refer to the 20-minute elaborate presentation, which is available on YouTube. Finally, if you have any questions, you can reach out to us via email. And I now look forward to your questions. Thank you.
Okay, thank you, Nimisha. Any questions here? I have a question with regards to the assumptions you need to make for this attack. For performing this attack. So did I understand correctly that actually you could, so or could you elaborate on which assumptions you need to make for performing?
So the basic assumptions are inconsistent with logic locking in general. So logic locking, attacks on logic locking require traditionally an oracle, which is nothing but a working chip. Like you require a black box access to where you can provide the inputs and obtain the outputs. So that's one access which we require. And another thing which we require is the reverse engineered locked netlist, so that we understand the internal structure, whether the black box which we were considering has AND gates, OR gates, NAND gates, and so on and so forth. But we don't, by this reverse engineered netlist, we don't obtain the original design, because now, as you can see here, it has been obfuscated by adding these gates. So without the correct information, you will not know what is the functionality of the design. Let's say we were applying all zeros here, the output would have been 0. But now for an incorrect key, the output can very well be 1. So without knowing the secret key, you cannot derive the original functionality of the design.
Okay.
So that's what we aim to achieve through the attacks. One is circuit recovery, and the other one is key recovery.
Okay. And so the attacker is assumed to be some manufacturer in the middle of the process, right? So he doesn't have the functioning chip yet. The
Yes,
final
yes,
product,
yes.
right?
So the attacker can be considered the foundry who has access to the locked design with the key gates sprinkled in the design. And the attacker can also be considered an end user who now has access to the working chip with the correct key loaded in the design. So now the attacker can collude, or the end user itself can reverse engineer the netlist to obtain the locked design. And then once that is done, the end user who has access to the oracle can apply some input patterns, obtain the correct responses, and then map these correct responses to the reverse engineered locked list which they have.
Okay, cool.
Okay.
Okay, thank you very much. Yeah, if anybody still has some questions, maybe we can all move to the social rooms, because I think now it's going to come a break. Yeah, I apologize that we went a little bit longer. But yeah, thanks everyone for the attention, and thanks all the speakers for your talks.
Thank you, everyone.